Hello everyone and welcome to tonight's stream. So today I plan on covering 211 and 212. In this case we have completed chapter 2 and what we're doing now is we're just reading the last sections of it. What happens here is that it's a very small section and depending on how long it's going to take to get through these two, I'm hoping to start chapter 3. Alright. So the usual rules apply. The book, you can download it. It's in the video description. And it's a book of proof, 3rd edition by Richard Hammock. The download is free. It's part of the Creative Commons. And I am going to read the book and then do the questions. But in this case, there's no questions in this part. So let's just get to it. But I will show examples on whatever they have for us to do. I got a feeling it's mostly going to be summary and pro tips kind of a thing. Okay, a logical inference. Suppose we know that a conditional statement P implies Q is true. So we know that P implies Q is true. This tells us that whenever P is true, Q is also true. But by itself, P implies Q being true does not tell us whether P or Q is true. Because remember, on an implication, I said this many times now, but think of it as cause and effect. If the effect happens, we don't care if the cause is false. We really care only about the effect, but the structure of it is like a cause and effect type of thing. But all we care about is the effect. So as long as Q is true, then the P can be false. Anyway, getting back to this, by itself, P implies Q being true does not tell us whether P or Q is true. They could both be false. On an implication, if both are false, the statement is still true. Think of it as being unchallenged. That's just my own addition there. Or P could be false and Q could be true. And that would also be true because, again, we don't care about the P, we care about the Q. But if in addition we happen to know that P is true, then Q must be true if the statement is true. Because, think about it. If P is true, but Q is false, well, then in that case, the whole statement cannot be true. That would be a contradiction because according to the truth table, it has to be false if P is true but Q is false. Now, but if in addition we happen to know that if P is true, Q must be true. This is called logical inference. From two true statements, we infer that a third true statement is true. So, in essence, statements P implies Q and P are added together to get Q. We can indicate this by stacking P implies Q and P one on top of another with a line separating them from Q. The intended meaning is that P implied Q combined with P produces Q. So we're going to say this. P implies Q. This is logical stacking. P gives us Q. And now, again, if we happen to know if we happen to know that this is true, P implies Q is true, and we know that P is true, then Q must be true, basically. That's what they're saying. All right, now, also, fun fact, if we know that this is true, and we know that P is false, then Q has to be false. Although, hold on a minute, let me think about this for a minute. No, it could be false or true. It could be false because if they're both false, the first statement would be true. It could also be true if P is false. So in this case, it could be false or true. That we don't know what the Q is. But since in this particular example they used, this is true, this has to be true for the previous two to be true. So we narrowed down what the Q is. This is very frequently used pattern of thought. In fact, it is exactly the pattern we used in example on page 34. Let's go to 34 first. That's a while back. It's all the way in chapter 1. Okay, I'm not sure which one they're referring to. But there's a bunch of different examples they used, such as root 2 is not in the integers. I think, yeah, I don't know. anyway, how the natural set is a subset of the integer set. Let's just continue here. All right. This is let's see here. This rule even has a name. It is called modus ponens. So. All right. Two other logical inferences called modus tollens and elimination are listed below. So let's just, not what I want. All right. I'm just going to write them out. Modus ponens tells us Q if P implies Q and then P. Now, this tells us that P implies Q, and if we know what not Q is, it'll tell us what not P is. Okay? And then on the last one is elimination. Okay, so elimination is P or Q, and then we take the not P, and so then it has to be Q. So basically, if it's P or Q, it's P or Q or both, right? And if it's not P, well, then it has to be Q. Now, if P implies Q, and it's not Q in modus tollens, then the answer has to be not P. So yeah, and if it's P implies Q, and if it's P, then the answer is Q. So yeah, that's and again, what happens is you have to know what the truth value is in that case, whether it's true or false, and you apply. So if modus tollens we get, for instance, P implies Q, and then it has to be not Q. So it's not P. If P happened to be true, then it's going to be not true, basically. That's kind of how we do it, at least as I understand it. It is important to internalize these rules. You already use at least modus ponens and elimination in daily life anyway. But you need to not remember their names. Few mathematicians can recall the names, though they use the rules constantly. The names are not important, but the rules are. And that's actually very true. We remember that what we use. We retain those skills, that knowledge, what we have to continue working with and using. So, like, personally, and I've realized this a while back, right? If you want to have something in your life, you have to structure your life around it. Like, it's very important for me to be fit and athletic, so I've structured my life with being an athlete. So that's just like why I work as a landscaper and a handyman, and I'm also a skating coach. Those things keep me active. I know that fundamentally I'd have a different body if I sat behind a desk all day. So it's just one of those things. So if you want any kind of skill, if you want to have it, the easiest way to do it, like for instance, if you want to learn a new language, easiest way to do it is to immerse yourself into that culture and be around people that speak that language and native speakers, and you would pick it up faster than just like 15 minutes a day here and there. And it comes down to how badly you want something and whether it's realistic for you to structure life around it or not. But anyway, that's my take on that. Let's just continue here. 3 additional logical inferences are listed below. The first states the obvious fact that if P and Q are both true, then so is the statement P and Q. So if P and Q are true, then it's also, so here we go. We're going to say, These are new statements. We're going to say P, Q, and so if the P is true and the Q is true, then it's P and Q. Sorry, I'm a little tired. Anyway, yawning here. All right, so then let's see here. The first states the obvious fact that both are true, so is the statement P and Q. On the other hand, P and Q being true forces P and also Q to be true. So if we have this, if that's true, then both P and Q have to be true. So the way they wrote it is P and Q, but in parentheses they mentioned it would have to be both. So in this case, they wrote P, but it also implies that Q would also have to be true. Okay, so this is an interesting one. Finally, if P is true, then P or Q must be true no matter what the statement Q is. That's very interesting. Yeah, if you think about it, if at least one of them is right, then P or Q is a true statement. These inferences are so intuitively obvious that they scarcely need to be mentioned. However, they represent certain patterns of reasoning that we will frequently apply to sentences and proofs, so we should be cognizant of the fact that we are using them. All right, so let's just at least remember this page. So this is the end of chapter 2, page 63, 64. Okay, so we might have to come back when we start writing proofs. We have another, I don't know, 50 or so pages to get through before we hit the next part, chapter 3. Yeah, sorry. Part 2 starts on page 112. Let's see here. Starts on 113. Okay. Okay, so now this is just they gave us no examples to work with. There are like a lot of that stuff they're saying it's intuitive. You normally use it, so just keep it in the back of your head. For us, we'll be using that when we start writing proofs. The way we structure the proofs will be used in some of those arguments. Now, 212. It is important to be aware of the reasons that we study logic. There are 3 very significant reasons. First, the truth tables we study tell us the exact meanings of the words such as and, or, not, and so on. For instance, whether we use or read the if, then construction in a mathematical context, logic tells us exactly what is meant. And that's an implication, by the way. If P then Q is an implication one. So that's P implies Q. Now, let's see here. Second, the rules of inference provide a system in which we can produce new information, or statements, from known information. Finally, logical rules such as De Morgan laws help us correctly change certain statements into potentially more useful statements with the same meaning. Thus, logic helps us understand the meanings of statements, and it also produces new meaningful statements. Logic is the glue that holds the strings of statements together and pins down the exact meaning of certain key phrases, such as the if, then, or for, all constructions. Logic is the common language that all mathematicians use, so we must have a firm grip on it in order to write and understand mathematics. But despite its fundamental role, logic's place is in the background of what we do, not the forefront. From here on, the beautiful symbols and, or, implies, if and only if, not, the universal quantifier, and the existential quantifier are rarely written. But we are aware of their meanings constantly. When reading or writing a sentence involving mathematics, we parse it with these symbols, either mentally or on scratch paper, so as to understand the true and unambiguous meaning. So, let's just write these down one last time for old time's sake. So, parting letter. We have and implies if and only if not for all okay. Just gonna change that to lowercase exists. All right, so those are the symbols that we've been working with. I just want to check on something real quick here. So yeah, no, this was a fun chapter. I meant like the whole chapter, not just the not just what we did today. A lot of the stuff is just it's very useful, and we're just gonna keep using it going forward. I'm just leafing through all the stuff that we did. It is very dense, and it was a lot of fun getting to this point that we're now entering yet again another chapter. So all right, that's it for this stream. And yeah, if you have any questions, yeah, just leave it in the comments, and then we will start on chapter 3, counting, in the next stream.